Hello, my name is Miguel Angel, and I'm going to present my work, a bilevel framework for decision-making under uncertainty with contextual information. I join work with Juan Miguel Morales and Salvador Pineda. We are all from the Oasis Research Group and the University of Malaga. My presentation outline is as follows. I'm going to first analyze several frameworks for decision-making under uncertainty, and I'm going to propose a new bilevel framework. I'm going to analyze how to deal with this bilevel formulation. I'm going to present a case study with an energy producer and a Cournot model. I'm going to show some numerical results and withdraw some relevant conclusions. My problem of interest is to minimize the expected value of an objective function f, where some contextual information is available at the moment of making the decision, where y is the uncertain parameter and z is a vector of decision variables. We can follow a predict optimize approach in which we use a model G as a function of the contextual information and with some parameter W to model the uncertain parameter Y. We can train this model with a data set to obtain the optimal parameter W that then we can use to produce a forecast for an unseen period T. Then this endpoint forecast is used in the deterministic counterpart of this problem to obtain the decision for that period. Another way of proceed, a decision learning approach, is to, instead of making a model of the uncertain parameter, we directly compute a model of the decision. We again train our model with a data set, but this time the function is aware of the objective function. Then we can directly compute the decision for the unseen period, evaluating the model with the parameters W computed this way. We here formalize a framework of each type. In the first case, in the predictive approach, we have a loss function that tries to that penalize the output of the model when it's not similar to the uncertain parameter. This way we try to compute the optimal parameter that produce a model that is similar to this uncertain parameter. Then we use a deterministic counterpart to compute the decision. In the case of the decision rule approach proposed by Van and Rudy in the Big Data News Vendor, we directly replace in the objective function the decision variable by a linear decision rule. And then we can just compute the decision for an unseen period evaluating this model. We proposed a third approach, a bilevel prescriptive approach that also aims to produce an uncertain, a model of the uncertain parameter y, but this time use a bilevel structure where the lower level tries to produce decision set that minimize the upper level objective function. Again, we can compute the offer for an unseen period, solving the deterministic version where we replace the model, computed this way. We use as benchmark method the deterministic counterpart of the problem, where we assume that we know with certainty the uncertain parameter. Comparing the predictive approach with the bilevel prescriptive approach, in the first case, it normally performs well in most tasks because we generally use a general loss function. Therefore, it's simple, but as we use a general loss function, we achieve suboptimal decision. In the case of the bilevel prescriptive approach, as we are considering the objective function of the original problem, it yields better decision, but is more complex and have some issues um, for linear objective functions. To build some intuition, we can say that the bilevel prescriptive approach focus on learning the point where a deviation could be costlier or could have a greater impact on the objective function. This bilevel model, we can expand or express in more detail the feasible set, and there are many ways to deal with this bilevel structure. We assume that strong duality holds, and then we can replace the label level by this KKT optimality condition, where we have the stationarity condition, primal feasibility, dual feasibility, and complementary slackness. This complementary slackness involves a product of continuous variables, and there are several ways of approaching it. We can follow a regularization approach, where we iteratively solve this problem, or we replace this constraint by this other one, and we iteratively solve the resulting model with epsilon, with decreasing epsilon. Alternatively, we can replace this complementary slackness by a big M reformulation, where we introduce some binary bilevel and the M are sufficiently large constants. We are going to analyze the performance of the different frameworks in the case of a Cournot energy producer. We want to maximize the revenues of the energy producer, that are the difference between the cost of the energy producer and the incomes obtained. We have chosen a quadratic cost function, and we model the price and offer relationship as a linear function. After some math, the model yields this more compact formulation where Q is the optimal offer. To see better where this linear relationship, what this linear relationship represents, we assume that the energy producer wants to learn the residual demand. In an energy market, we have the offer of the competitors, and we have the offers of the consumers. The residual demand can compute it as the difference between these two curves, where here we have small prices, and therefore we have more demand than offer, and here we have less demand than offer, and we have higher prices. Our producer is interested in this part where we have more demand than offer, so we have some margin to produce energy. We try to approximate this residual demand by this linear relationship P in a neighborhood delta. Therefore, our problem is to find the optimal offer Q star that maximize the revenues of the energy producer. In this case study, we have made the assumption that our behavior does not influence the rest of the competitors. Our offer is just a single quantity. The transmission grid is neglected, and a linear function can approximate the residual demand. Our benchmark approach is the deterministic problem, in which we assume that we know with certainty the uncertain parameter, the market uncertain parameter, beta and alpha. But before introducing the rest of the framework, we perform a small trick in which we reduce the number of uncertain parameters divided by beta, and we obtain this gamma parameter. We use a linear model that is some regressor associated with some contextual information. And here we present the three models applied to this case study. In the first case, the training step yields a standard linear relation, a standard linear regression with the squared second norm, and we are just trying to learn the uncertain parameter gamma that we then use in the deterministic problem to compute the optimal offer. In the bilevel prescriptive bilevel approach, we use the original problem in the upper level because we cannot perform this trick with the summating, and we use the objective function with reduced number of uncertain parameter in the lower level. This way, we can compute, we can train a model for this uncertain parameter gamma that yields good decisions. Again, we compute the decision for an unseen period, replacing the uncertain parameter by the model computed this way. In the case of the decision rule, we replace the quantity by the offer by the linear decision rule, and we just evaluate this model for the unseen period. The KKT reformulation is as follows. We have the stationarity condition, primal feasibility, dual feasibility, and we have two alternatives. The regularization approach that yields a non-linear optimization problem that we use Cournot to solve it, and the big M approach that yields a mixed integral quadratic programming where we can use triplex to solve it. In the first case is fast, but doesn't guarantee optimality. But in the second case, we achieve optimality, but is slow, and we have the issue of tuning the big M's. We illustrate the performance of the different models in a case study where we have a training set of historical market data that we use to compute the uncertain parameter alpha and beta, and we have some contextual information that in this case is the wind and solar power production that we use to explain this uncertain parameter. We consider different technologies in this case. In this case study, the parameter C1 of the cost function represent like the cost of the energy field of the energy producer of the power plant, and this represent the capacity. We have different cases. For example, a base power plant has a low fuel cost and a high capacity, while a peak power plant has a high energy cost and a low capacity. We keep the quadratic cost fixed in this case study. We can compute in this chart the optimal offer for all the data points of the training set, and we depict the percentage of the point that this optimal offer is equal to 0, between 0 and maximum capacity, or equal to maximum capacity. We can see that in the case of the base power plant, most of the offers are equal to maximum capacity, while as we move towards a peak power plant, most of the offer are equal to 0. We show in this chart the percentage of the income compared to the benchmark method of the three approaches for the three types of technologies: base, medium, and peak power plants. We can see that our approach outperformed the rest of the approaches in all three cases, but the difference increases as we move toward peak power plants, where and the fuel cost is higher, and we have fewer offers different than zero. Also, it's interesting to remark that the decision rule approach incurs in some infeasibility points in the test set. To finish our presentation, we remark that we have proposed a bilevel framework for the decision-making under a new bilevel framework for decision-making under uncertainty. We have shown how to apply all the three frameworks into the case of an energy producer with a Cournot model, and we show that our method outperformed the other approaches in a realistic or numerical example. Thank you for attending my presentation. And if you have if you want to see more about this work, you can check my preprint that I attached below, and I'll be happy to answer any of your questions. Thank you.